the AIME problem number 3. That's the American Invitational Mathematical Examination. And there's a very powerful substitution here that I want to talk to you about that I don't think anybody noticed as far as the people who took the test or the people who actually posted the solutions. And somebody by the name of Elaine Dawe figured it out. And I just want to mention that name, just that's it, because this is impressive. I never thought of it. None of the problem solvers thought of it that I know of. And none of the solution posters noticed this nice idea that involves a substitution. So what a lot of people did is they made a substitution without the radical. But what's going on right here that makes this problem work out so nicely. Now, let me talk about why the substitution is a good idea. The standard approach and a number of people at Quora and Math Exchange, you square both sides, but you end up with a fourth degree equation. If you square the left-hand side here, you end up with x to the fourth power. And then you get rid of the radical, but you still have a fourth degree quartic equation that you have to solve, which is very difficult. And you need some tricks or a long, nasty formula. So it turns out this substitution right here just works wonders. Now, if you take a look here, what she chose to do is just take y equal to this circled object right here. Okay. Now, of course, if y is equal to this, then y squared is just equal to the radicand itself, which is x squared plus 23x. And I can't believe, I looked at this forever, I never noticed it, and nobody else did that I know of. All right, so again, just as simple as it can be, but nobody noticed it. But again, you said y equal to this, if you square it, you get the radicand. But notice that turns this entire monster into this expression right here. And that's what really makes this so incredible. I mean, some really bright people squared all of this out, went to a lot of work, and then they had to reject the extraneous solutions. This is the way to do it. There's no doubt about it. So if you let y equals this equation, 57 minus 27 is the 30 that you see right here, right? So isn't that amazing? And it turns out this thing factors nicely. I didn't show the factorization, but if you factor it, you'll get y minus 9 and y plus 3. And that leads to the solutions y equals 9 or negative 3. Now, because of the substitution, we always wonder what to do with these negative numbers. All right. Well, again, y is the square root of something, right? So the square root of anything has a range that's non-negative, right? So we have to reject negative 3 equals to the square root. However, we can go ahead and use 9. Now, right here, folks, if we let 9 equal this, and you square both sides, you get 81 equals to the radicand. Okay, plus 57, and then of course that leads to that very next statement. All right. If you subtract 81 from 57, you get negative 24. And so by inspection, without knowing what the actual real roots are, we know that their product has to be negative 24. Okay, some people call that Vietas, but you really don't have to mess with that, because if you have a quadratic expression and you write the linear factors out like this, x minus, we'll say R1 times x minus R2, R sub 2, okay, equals to 0. Notice what happens here. These, without thinking of Vietas, these minus signs cancel. A minus times a minus is a plus. All right, and so that means that if you inspect this constant term right here, you get that minus 24 has to equal to the product of the real zeros. In a lot of ways, it wasn't necessary to say they had to be real zeros because the math just takes care of it. But there you go, ladies and gentlemen. Negative 24 is the product. It's the answer right here. Negative 24 is the product of the roots or the zeros without looking at them. And also, just one last thing, if you have any doubts about this them being real valued, the discriminant of this expression is positive. 23 squared minus 4 times negative 24 is a positive number. And so the discriminant is positive, indicating two distinct real roots, and their product is negative 24.